Hi everyone, I'm Daniel. I'm here to talk about how we find outflows in the DUVET survey. But first of all, I'd just like to take a step back and talk about why we might even want to in the first place. So if you study outflows, feel free to check your email for the next minute. So this is the galaxy stellar mass function, which describes the number density of galaxies at different masses. And what we're showing here is in the process of gas falling into galaxies and making stars, if we just include gravity, then we make things that are way too big. And so we really need some mechanism to slow this down, perhaps by removing mass from galaxies. The high end of this discrepancy we think is caused by AGNs, but for this talk in particular, I'm specifically interested in that low mass end. Unfortunately, in observations of star-forming galaxies, we see with great frequency this phenomena of galaxy scale outflows. This is M82. You've seen this a few times now. It's a nearby edge on starburst with probably the most well-studied outflow. And so we can start to think about how we might get an outflow going, and one way that we know of to do that is with supernovae. So we have this model where a star explodes and this hot expanding wind pushes gas up out of the galaxy disk and into the halo. And to zeroth order, this is definitely what's happening, but we know the galaxies are pretty complex, and there's probably quite a bit of secondary behavior that we don't capture with this simple model. And in addition, the observations that we do have in our results from simulations all have to make assumptions about the basic properties of outflows, since the sample of galaxies for which we have resolved outflow observations is really small. I'm showing here star formation rate on the y-axis and stellar mass on the x-axis, and the shaded region is the SDSS sample of galaxies. And these colored points are the galaxies for which we have resolved outflow observations. It's not very many, and in particular, I just want to draw our attention to the red squares, since they're the ones at redshift 0. And that's where we start to get a sub-kiloparsec resolution. And since we expect that the properties of outflows are likely changing on sub-kiloparsec scales, all of our simulations are being constrained by maybe 5 galaxies. So that's not great. And particularly at the low mass end, this is a real problem, since we expect that the properties of galaxies, of outflows, are dependent on the property of the galaxy, on the properties of the galaxy. Fortunately, with the recent advent of image slicer IFUs like MUSE on VLT and KCW on Keck, we're starting to enter this era where we can potentially have these large IFU surveys of outflows, which is pretty cool. And so what I'm particularly interested in, first of all, is how we can identify outflows. As we move into this new era, what we really need, we run into this problem where just detecting the outflow is perhaps not the problem it may once have been, but we also find all of this other surrounding gas. So we need new methods for distinguishing the outflow from the surrounding gas. And in previous studies of individual galaxies, the determination of what constituted an outflow was done in a much more ad hoc way. But as our data sets get larger and we start looking at samples of galaxies, what we really need are systematized methods that we can apply automatically to larger samples of galaxies. And then once we know where the outflow is, I'm curious about where the mass is within that outflow, since one of the failings of this very simple hot expanding wind model is in its prediction of the mass profile in the outflow. And so a step in the direction of increasing the number of galaxies for which we have these resolved outflow observations is the DUVET survey. You've heard about that previously, but of particular interest to me are the large number of edge-on nearby low metallicity galaxies with very prominent outflows. And one such galaxy is Decaying 1486. It's an edge-on low metallicity starburst at low redshift. And we can see in this H-alpha imaging this extended filamentary structure that looks quite a lot like outflow. And so we can use Decaying 1486 as a test case to start to develop some of these methods for distinguishing outflows. The thing about how small the sample is of galaxies for which we have these observations is that every galaxy we add to this sample has the potential to really teach us something new about outflows. And so I just want to run through a few of the results that we have on Decaying 1486. This is a result you saw previously. This is from a paper by Alex Cameron based on DUVET observations, which I led the data reduction as the first project of my PhD. And in this work, they're able to map metallicity in the disk and the surrounding gas using the oxygen 34363 line. Auroral lines like 4363 are a much more robust way for measuring metallicity, since they don't have the secondary dependence on other gas properties that we might run into with strong line ratios. So we can measure the metallicity in the disk and the surrounding gas using the same metric. And so there's this question in CGM study about how different the gas is between inflows and outflows. we expect from this rough model we have of the baryon cycle that galaxies are accreting pristine gas from the IgM along the major axis and expelling processed metal-enriched gas along the minor axis. And in the results of this work, we find roughly 3% solar metallicity entering the galaxy via inflows and roughly 15% solar metallicity exiting the galaxy. So that gives us a metal loading factor of roughly 5 times. And this metal loading factor is a direct input into every simulation that takes this into account. And prior to this work, basically no results measuring it. So this is really cool work that isolates this galaxy's contribution to the baryon cycle and demonstrates the enrichment of gas in an individual galaxy. We can also have a quick look at the surface brightness profile in Decaying 1486. This is in oxygen 35007. It's just the brightest emission line in our observations. We've got flux on the y-axis and minor axis offset on the x-axis, and we fit the flux-weighted surface brightness profile with a double exponential just to demonstrate this extended emission. And the takeaway here is just that, yes, we do have this extended emission that we would expect from the galaxy with an extended outflow. We can also have a look at how the galaxy and the gas surrounding it is rotating. So these are rows parallel to the galaxy disk out along the outflow at 3 different minor axis offsets. And we can see that the gas stops rotating very quickly in the first 1 to 2 kiloparsecs. And so to give some context to that, I have these 2 scenarios over here on the right. One where the galaxy is blasting gas out everywhere perpendicular to the galaxy disk. And in this case, we should expect that the gas should maintain the angular momentum of where it's launched from. So the outflow should be rotating in this case. And this other option is we have a galaxy that's pushing gas out from the central regions with a wide opening angle. And here, conservation of angular momentum just means that as the gas moves radially out from the galaxy center, the rotation should slow. So what this result implies is that the outflow in Decaying 1486 is being launched from the central regions with a wide opening angle. We can also have a quick look at the velocity dispersion in the disk and the surrounding gas. And again, this is in the oxygen 35007 emission line. And we can see the low dispersion disk right at the center of the image. We can see that dispersion increase really rapidly as we start to leave the disk along the minor axis direction, and it remains elevated right the way to the edge of the image. And so we can use this velocity dispersion to distinguish the disk from the surrounding gas. It's pretty cool. So we can start to build up this model of outflows as bipolar minor axis nebula surrounding a starbursting source with an extended surface brightness profile that's also kinematically decoupled from the disk. And then based on this model, what we've done is written some software that we can apply automatically to galaxy observations. We basically take the single Gaussian dispersion to define the disk region and then step off in the minor axis direction to find the brightest spaxel in each row and take the median position of those spaxels to find the center of the outflow. We define that as the center of the outflow. And then we find the 50 and 90% widths either side of that line in terms of surface brightness and define that as our outflow region. And this is a technique that we can start to apply really automatically to larger samples of galaxies. And that's exactly what we intend to do next. And so once we know where the outflow is, we can start to think about where the mass is within that outflow. And so here's 4 models of the minor axis mass outflow rate profile differentiated by our assumptions about electron density and outflow velocity. Since this galaxy is really edge on, we get no information about outflow velocity. It seems to max out somewhere between 150 and 460 kilometers per second based on the literature. And electron density, really hard to measure in this galaxy. All the optical emission line traces are at or below the low density limit for that. So we can't measure it in this galaxy pretty much in the outflow. But we can make some assumptions. And so the bottom 2 are assuming a constant electron density, and they're differentiated by their assumptions about outflow velocity. And the upper 2 models are assuming a decaying electron density. And this much flatter mass outflow rate profile that we recover there is more consistent with what we expect from simulations in the ionized gas. But what we can really take from this is that the electron density and our assumptions about it have a huge impact on where we think the mass is within the outflow, whereas our assumptions about outflow velocity, not so much. So what this means we need, since we're about to have tens of galaxies for which we have these kinds of observations, is for simulations to run radiative transfer modeling so that we can compare their outputs with things we can measure directly, like surface brightness. And so I've talked quite a lot about the inner part of the outflow. But there's also this question about how it's interacting with CGM beyond this. And I get the strangest feeling that we're going to hear something about that soon. Thank you.
Thank you.